Okay, so notes 4 is confidence intervals for a difference in means. The beginning of this notes is a recap, kind of like majority of the notes we went over so far in this unit. So starting with sampling distribution of a difference in means. Remember, when it talks about shape, center, and spread, it's actually making an inference to our three conditions. So shape is talking about if it's normal. What is center telling us? Not independence. What's the other one? Random. Okay, remember, we have to prove that something is random in order to find our center or our mean. We talked about that beginning of the year. Okay, and then spread is independence, which means we have to prove that a sample is independent in order to find standard deviation. Okay, so for the shape, we still want this to be approximately normal. And we use what theorem to prove that? CLT, the central limit theorem. Since we have two samples, though, that means both samples have to be greater than or equal to 30. If one of them is not greater than or equal to 30, then you have to graph the histogram. Okay, if both of them are not greater than or equal to 30, then you're going to graph how many histograms? 2. Okay. If one or both are less than 30, each population should be normal. Okay. What that means is when you graph the histograms and we are trying to determine if it has no outliers or extreme skewness, we're trying to prove that the population for each of the sample is approximately normal. Okay, for center, since we have two samples, we're talking about two centers. So we have mu of x1 bar, which is mu1, and mu of x2 bar, which is mu2. So if we're taking the difference of the two means, mu of x1 bar minus x2 bar is the same as just saying mu1 minus mu2. Okay. Since this is the random condition, that tells us that both samples must be what? Randomly, what's the first one? Selected. So randomly selected, which means we are dealing with a sample, okay, or sampling distribution. Or what's the other one? Randomly assigned, and we would know it's randomly assigned if we were dealing with what? An experiment. Okay, so again, just to recap, I don't know how many times we've probably wrote these conditions down every notes. For independence, we're talking about spread or standard deviation. So we have sigma of x1 bar is equal to sigma 1 divided by the square root of n1, and sigma x2 bar is equal to sigma 2 divided by the square root of n2. So if we're doing the difference of two standard deviations, remember we never subtract them, so we're going to do what instead? Instead of subtracting the standard deviations, we're going to add them. Okay, so that means sigma of x1 bar minus x2 bar is the same as taking the square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. We always add our standard deviations together. We are able to find standard deviation and prove independence as long as which condition is met? 10% condition. Okay, the 10% condition, since we have two samples, have to be met for both samples. So we have to do N1 is less than or equal to 10% of population 1, and N2 is less than or equal to 10% of population 2. The only time we do not check independence is when we are doing what? An experiment, right? In an experiment, we do not check independence, which means we do not check the 10% condition. Okay. Any questions so far? The next part is standard error, and what that means is we need to use S to estimate sigma, because when we're dealing with the FRQ, or type of inference, we don't always know sigma, so we have to estimate it by using the sampling standard deviation S, which means instead of having the equation above for a spread, we have this equation instead. S of x1 bar minus x2 bar is equal to the square root of s1 squared divided by n1 plus s2 squared divided by n2. Okay, notice it's the exact same equation, but instead of sigma, we use S. Okay, and that takes us to degrees of freedom. So remember, when we did one sample, we had a degrees of freedom formula of what? N minus 1. Well, now that we have two samples, our degrees of freedom formula is this. Okay, this long formula. However, we have Desmos, right? You don't need to know that formula. We have Desmos. I'm gonna show you how to find it on Desmos. Okay, that's one option of finding the degrees of freedom formula, or sorry, degrees of freedom number is by option 1 using the formula. Okay, technically option 2 is use the calculator, which we're going to do on Desmos. And then option 3 is using the conservative method. And so what it means by the conservative method is that we look at both sample sizes and we take the degrees of freedom for each one and then take the smallest of the two. So we're going to take the smaller degrees of freedom from both samples. So that would be like saying sample 1 minus 1 and then sample 2 minus 1. Okay, so for example, let's say N1 was 10 and N2 is 8. So if we did 10 minus 1, we would have degrees of freedom of 9. And 8 minus 1, we would have degrees of freedom of 7. So if we want the smaller of the two, which one would we take? 7, the degrees of freedom from N2, which would be 7. The only problem with this, and this is why it's called the conservative method, is that when we do that, when we choose the smaller of the two sample sizes to find degrees of freedom, we end up with a confidence interval that is very large. So it makes sense. Confidence intervals will have a margin of error that is very large. Cross-off is needed. Okay, and then the significance test is going to give us a p-value that is greater than the true p-value. And so it's called conservative because we want to make sure that our answer is going to fall in those intervals. So for a confidence interval, we make it very large, so our answer will fall into that. For a significance test, we increase the p-value so we can make sure we have some significance to defer from the problem. However, would this be a good depiction of the data using this conservative method? No. Okay, so you will never use this method because you have Desmos, right? This is reserved for when you do not have access to a calculator, which you always will. Okay. I would think of this as maybe a multiple choice question, like if you're using the conservative method, what happens to the confidence interval? Okay, what happens to the p-value in a significance test? You would just have to know that relationship, not necessarily use this method. Okay. Then again, talking about the conditions for this inference, same thing that we repeated on the very beginning of the notes, that for random, we have to either show that both samples are random and or show that both are randomly assigned. So we have two treatments if we have two samples. Independence, we check the 10% condition on both samples unless we're doing an experiment. And then for normality, we're trying to prove that both populations are approximately normal. So we're going to use the central limit theorem to prove that. If they are less than 30, we are going to graph histograms and check for outliers and extreme skewness. Okay, so there's nothing really to write here. It's just a recap of what we just wrote down. Okay, so then now that brings us to two sample t interval for a difference between two means. This is technically the name of the inference, but when we're doing the example FRQ, I'm going to write it in shorthand so you don't have to write that whole thing. So remember, for each inference, we're given a formula. We don't have to use the formula because we have Desmos. So it says when the conditions are met, an approximate C% confidence interval for mu1 minus mu2 is the following. So we have x1 bar minus x2 bar plus or minus t star times the square root of s1 squared divided by n1 plus s2 squared divided by n2. Okay, notice this is following the same pattern as you see on the formula chart. It is your test statistics, so in this case, it's the difference in means, x1 bar minus x2 bar, plus or minus your critical value, in this case, it's t star, and then times your standard deviation, which in this case is your standard error. Do you need to show this formula on the FRQ? No.
What's the equation called?
Two sample t interval for difference between two means. That big, long, yeah.
That's great.
Okay. Now we're going to look at the FRQ. And what's interesting about this FRQ is that there has not been another FRQ like it on the AP exam since 2006. Okay, so before a lot of you were even born was the last time this showed up on the AP exam. Which can mean one of two things. It can mean that, oh, they're like, it's been 20-something years, right? Let's go ahead and bring it back. Or they could think, well, it's been 20 years, we haven't used it, we're going to phase it out anyway. So what I think that they're going to do is I think they're going to do not have something like this on the AP exam because they're changing the curriculum next year. Okay. However, you will be tested on this regardless for the unit exam. Okay, you just won't have to worry about it when we're reviewing for the AP exam. So for this FRQ, it says an observational study suggests that drinking at least 4 cups of coffee a day reduces strokes. This is believed to be because coffee contains a range of plant-based compounds called polyphenols, thought to promote healthy blood vessels and dampen inflammation. In an experiment, go ahead and highlight this, 20 healthy women were assigned at random to drink 3 cups of regular coffee a day or drink no coffee for 2 weeks. The level of polyphenols in their blood was measured before and after the 2-week period. Here are the percent changes, so before minus after, of the polyphenol levels for the subjects in both groups. So notice we have a group of people who drank coffee and a group of people who did not drink coffee. How many people are in each group? 10. So the first question says, why will we be creating a 2-sample t interval instead of finding the difference between the two and using a 1-sample t interval on the difference. So remember when we did the IQ lab, we were doing a matched pair study, which means we were comparing your guys' IQ to period 4's IQ, okay? And I anonymously labeled every student with a number. So student 1 from this class was matched up with student 1 from 4th period. And then you guys used that to compare your IQ. So that means everybody took the tests. The difference here is even though we had 20 people in our experiment, did all 20 do the coffee for 2 weeks and then no coffee for 2 weeks? Nope, only 10 of them did. So that means they were assigned to different what? Treatments. They were assigned to different treatments. So since this is an experiment where they were assigned to different treatments, that's why we're using a 2-sample versus a 1-sample. Okay, so we're going to write that this is not a matched pair design. Instead, each group was randomly assigned a treatment. Okay, so again, 10 women said you need to drink coffee for 2 weeks, at least 3 cups a day. Okay, the other 10 said no coffee at all, okay, for 2 weeks straight. Okay, then they collected their results. Okay, so that's the big difference between a 2-sample t interval and a 1-sample t interval for difference. Okay, part A is not part of the FRQ. It's just for us to stop and think and look at those inferences and know the difference between the two. Okay, the FRQ actually starts on part B. And part B says, construct and interpret a 90% confidence interval for the difference in mean percent changes in polyphenols levels for the coffee and no coffee treatments. So on Desmos, what I want you to do real quick is I want you to create 2 lists, one for coffee and one for no coffee. Okay, to make it easy to identify, instead of saying list 1, list 2, what could we call our first list? C for coffee. What about our second list? N for no coffee. Okay, I think it only allows you to do one variable, so you wouldn't be able to actually type in coffee or no coffee. But you could label it C and N. Okay, so go and take a minute and do that, and then we'll come back and start our confidence interval. Okay, and how many elements should you have in each list? 10. You should have 10 in each list. The biggest mistake that can happen is if you accidentally type in your numbers wrong. So make sure you're typing in the correct data. If you don't have your Chromebook, look off your besties. Well, not that bestie. He's doing something else. Okay, and when you're done typing in your 2 lists, go ahead and start on the communicate part. Remember, you have to first identify mu1 and mu2. Okay, so it looks like majority of you have your lists in. Okay, so if we first in our communicate establish our parameters, mu1 and mu2, mu1 is going to represent what?
Average level of polyphenols.
Average percent,
Oh.
because it mentions that each of these is the percent change. So the average percent change in polyphenol levels for coffee drinkers. And then mu2 should be the same except for
No. Coffee.
good non-coffee drinkers. Okay, remember when you are identifying your parameters, it should always be a sentence. And also make sure you're paying attention to the problem. So if the problem is talking about mean, you have to use mu. On homework 2, a lot of you are still putting P. P1 is equal to this. P2 is equal to this. That is only for proportion. Okay. Okay, then since it's a confidence interval, we're going to establish that this is a 90% confidence interval, which means we could calculate our T star value to be 1.83. Okay, and remember you would do that by going under probability distribution and click on T distribution and type in your confidence level. Okay. What else do we need for the communicate part? The mean? Yep, so you need x1 bar and x2 bar, which you would calculate on Desmos. Okay, what else would we need? Standard deviation, so S1 and S2. Okay, we're missing 2 more things. Good, N1, which is 10, and N2, which is 10. And then one last thing. Since we're doing a T distribution, we need to know degrees of freedom. So degrees of freedom, and for now, we're going to leave degrees of freedom blank, okay, because we're going to actually need Desmos to calculate that for us, unless you want to go do the formula. Okay, I suggest you don't. Don't do the formula.
They're both the same type of, you don't need to write it once.
Yeah, well, no, you always are going to have 1 degrees of freedom, always. So for the mean and standard deviation, remember you find those on Desmos. So I'm going to go to Desmos. I have my 2 lists already in here, and for my X bar, I'm going to go to functions. I'm going to click on mean, and I'm going to do mean for coffee drinkers, which I labeled C, and I got 5.19. And then go to functions again and do mean of N, which is my non-coffee drinkers, and I got 0.45. So we're typing that, or we're writing that all in on our communicate part. Then we need our standard deviation, which again, we're going to go to our functions and click on STDEV, standard deviation. Okay, for both the coffee drinkers and for the non-coffee drinkers. Okay, so notice I get 2.57 and 2.69. Okay, so I'm going to use all that data and fill it in. So for X bar 1, I got 5.19, X bar 2, 0.45, standard deviation 1 is 2.57, standard deviation 2, 2.69. Okay, the only thing I'm going to leave blank for now is standard deviation, and we'll come back to that in just a moment. Okay, any questions on communicate?
Actually, I do. Can you walk me through the Desmos, how to find the T star again?
Yes. Okay, so the question is how to find T star. So on a new line, I would go to add an inference. I would click on probability distribution. Oops, and it got off of it. Okay, so probability distribution, I go down to t distribution. And, oh, okay,
That's where I got it.
you would need the degrees of freedom. So I'll show you that once we find degrees of freedom.
Okay.
Yes, I forgot about that, but we will get to that part when we do the calculate. Okay. So on to conditions. Are we going to do all three conditions? No, which one are we skipping? Independence, because this is a experiment. So for conditions, we're first doing random. And in the problem, we highlighted where it said assigned at random. So that's what I'm going to write, assigned at random. Okay, that's enough to prove that I have random assignment for both treatments. Then I'm going to check normality. And both of my sample size is 10. Is 10 greater than or equal to 30? No, so I say since both N1 and N2 are less than 30, we graph. And how many graphs are we going to have to do? 2. Okay, so you're going to make 2 histograms. And then we're going to look at those histograms and describe if there's outliers or extreme skewness. Okay, so I'm going to walk you through that on Desmos. If you already know how to do the histogram, just go ahead and do that on your own. Okay, so the first step, remember, is to go to functions, scroll down to visualizations, click on histogram. And then I'm going to do the histogram for C, which is my coffee, and make sure my bin alignment is where? To the left. Okay, then I'm going to click on my histogram again for non-coffee drinkers. Make sure my bin alignment is to the left, and then I'm going to go find the bin width for each. What's the formula for bin width? Good. Range divided by the square root of n. So our range is our maximum minus our minimum value. So I have 8.4 minus 0.7. Okay, divided by the square root of 10, and I get 2.4, which means I'm going to check both 2 and 3. So 2, okay, looks good. I have 5. Okay, then I check 3, which is not good. I have 3 there. Okay, so I know it's going to be 2. Okay, then for the next bin width for no coffee, I'm still doing the maximum minus the minimum. So my maximum 4.1 minus my minimum, which is negative 3.8. Remember, minus a negative is plus a positive. Okay, divided by the square root of 10. And this time I get 2.49, which again, I'm going to check 2 and 3. Okay, so I have 2. Let me turn this one back on, that one off. Okay, so 2 looks good. I have 5 bins there. Still check 3 just in case. Again, that one doesn't look good. I only have 4 bins. So your bin width for both of them should be 2. Okay. Once you have both of them up there, you can actually click on the picture next to your histogram to hide one. So you can draw it and then go back and hide the other, draw the other one. Okay, so I'm going to take that and I'm going to draw my graphs here. Remember, it doesn't need to be precise, but you need to make sure you label everything. So I have my coffee and my no coffee. And then I have frequency. Your Y is always your frequency. And then how you decide to scale it is up to you. Okay, I would just copy what Desmos says. Again, does not need to be precise. Just make it the best you can. Okay, so I have my 2 histograms. Okay, so while you guys are copying this down, I'm going to talk a little bit about homework 2. So on homework 2, again, another big mistake I saw is when you guys drew your histograms, a lot of you only drew 4 bends. So if you see a 4 question mark, that means you didn't have enough bends. Okay, also, if some of you who did your bends correctly just forgot to label. So majority of you remembered to label Y. A lot of you just forgot to label X. Okay, so remember you need both labels. And if I saw that that was missing on your homework, then I just wrote label question mark. Okay, if your FRQ was all over the place, I probably put 4 C's question mark because you didn't organize it correctly. Okay, and then I didn't even bother looking through to see if your answer was right. Okay, if it didn't look like the 4 C's, I just wrote 4 C's question mark. Okay, so looking at these 2 histograms, do you see any outliers? No. Do you see extreme skewness? Nope, so we would say that wherever we can find space, let me just erase, so make my line go down a little further. So both graphs show no outliers and no extreme skewness. Okay, so that's enough for us to go on and move to calculate. Okay, any questions on conditions? Okay. So then on calculate, we need the name of our inference. Okay, and instead of writing that long title, where we can just write a 2 sample, because we have 2 samples, T, because we're using a T distribution, interval, because we're doing a confidence interval, for means, because we're using means and not proportions. Okay, which means when we get an answer, it's going to be an interval, so in something inside the parentheses. Okay, so when I go to Desmos, I'm still using my t-test. Okay, so I'm going to go to add an inference. I'm clicking on t-test. Oops, t-test. And I'm going to put in both my data lists. So for sample 1, I'm going to put in C for coffee. Then on sample 2, I'm going to put in N for no coffee. So C for sample 1, N for sample 2. Hit create tests. And then I'm doing a confidence interval at what % confidence level? 90. So I'm going to go to 0.90. And notice I get the interval 2.7 to 6.7. And then on that same thing, if I scroll down where it says significance tests, and I don't know why they put it down here, but if you go on to significance tests and on the diagram click on the 3 dots, that is where your degrees of freedom is. So you'll find degrees of freedom under the significant test tab. Okay, so we're actually going to write that degrees of freedom back in the communicate part. Okay, because we still have to establish what our degrees of freedom is. Okay, so going back to the FRQ, my degrees of freedom, because it calculated on Desmos, was 17.9641. If we were to use the conservative method, what would our degrees of freedom be? 9. Is 9 very different than 17.9? Yep, so we would have got answers that did not match up very well. And then for our answer in Calculate, we got 2.7? Yep, 2.7 and 6.7. And that's all we need in the Calculate portion. So now we can write the conclusion just like we always do. We start off by saying we are, so we are 90% confident that the true, what? That the true, are we doing mean or proportion? Mean. So mean, and then since we're doing difference, we have to say difference as well. Okay, that the true mean difference in polyphenol levels between coffee and no coffee is between 2.7 and 6.7. And notice my problem didn't contain any units, so I'm not going to write any units. Okay, but it would not be wrong if you said 2.7 units and 6.7 units. Okay, or even percent, because it's the difference in percent. So 2.7%, 6.7%. Okay. The last part here, part C, says, does the interval suggest that coffee is more effective at producing polyphenols? So this goes back to our lab yesterday where I told you guys if our interval contains 0, what did we say?
There's not conclusive evidence.
Good, there was not a significant difference, which means we could not, we don't have any convincing evidence for it. So if we look at our confidence interval, does our interval contain 0? So what does that tell us? Good, that there is a significant difference. So if we were answering this problem, what would we say?
In our confidence interval.
Since our interval doesn't contain 0, we said that means it is a significant difference. That means this suggests that coffee is more effective at producing polyphenols. So if 0 was in our interval, we would make the conclusion that what? That coffee is not more effective at producing polyphenols.